Thank you very much. And as Paul said, I'd like to talk about past, present and future climate, and I'd like to acknowledge the contributions some of my colleagues have made, both at the Centre for Applied Climate Sciences, but also Lynette Bettier from Bureau of Meteorology, who used to live in Benalla. And I'm going to draw on a number of sources, and the main sources are the latest IPCC report. IPCC stands for Intergovernmental Panel on Climate Change. We'll also draw on information from the State of Climate report put out by CSIRO and the Bureau every couple of years, and another report by the Victorian Government in conjunction with CSIRO on projections for the Goulburn region, as well as information from the Bureau website. And here's an overview of the talk I'd like to give. It's quite a simple talk. Just talk about two things. First, the past, and second, the future. And with the past, we'll reassure ourselves that climate variability is very important to climate in Australia, and including in the Goulburn Valley and adjacent regions. And then we'll look at how climate has changed over not just the past century, but even over the past thousands of years. And then we'll talk about what has caused those changes that have been observed. And then when we turn to the future, in addition to looking at what the outlook is for the next season, we'll also start to talk about what's projected for the coming decades out to the end of the current century. And so what this shows is a time series of the rainfall averaged over the whole country from 1900 through to the end of 2020. So each bar is the total amount of rainfall on average across the whole country received in millimetres. So you can see that there's a huge amount of variability. In some recent times when we set the low record, we had less than 300 millimetres of rainfall averaged across the whole country, so 0.3 metres. So I just ask if people could go on mute, thanks. Thank you very much. And then in other years, say in the mid-70s, which is a La Nina year, we had over 700 millimetres of rainfall. So there's more than a factor of 2 between the lowest and the highest, which is an incredible amount of variability. And if you look at near Shepparton, it's the same story. So you get lots of variability, a little bit of a weak trend down in the annual rainfall. But you can see that in some years, in fact, we set the low record, we set the low record of 200 millimetres in the early 2000s. Then you can see there have been previous periods when we received more, when Shepparton received more than 800 millimetres. So that's a factor of 4 between the lowest values and the highest values, which is an incredibly high amount of variability, which I'm sure you're all very used to dealing with. One of the reasons why we have such a high amount of variability is because of the El Nino Southern Oscillation, or ENSO, the El Nino Southern Oscillation. And this is a naturally occurring phenomenon centered in the tropical Pacific and exhibits 3 phases. And there's a blowfly. Hope you can't hear it. The El Nino phase, we have a neutral phase where not much is going on, and we have a La Nina phase. So if you like, it's a bit like a squeaky old swing or a spring. So it sort of flips back and forth between La Ninas, El Ninos in a very erratic, irregular manner. And on average, about half years are neutral years, about a quarter of years are El Nino years, and about a quarter of years are La Nina years as a rough average, but there's no regularity to the order in which they appear. And during La Nina years, you tend to get cooler waters in the central and eastern tropical Pacific, and you get major changes in the atmospheric circulation. So you get much stronger trade winds. You tend to get warmer water over our part of the Pacific and to the north of Australia, and that tends to increase the amount of rainfall that we receive in many parts, particularly in eastern Australia, especially during winter, spring. Whereas during El Nino, the opposite tends to occur. You get warmer waters in the equatorial Pacific in the centre and towards the east, and that drags that juicy convection with lots of rainfall away from our part of the world, and you tend to get lower than expected or lower than average rainfall. But it's not the only sorry, I'm having a little bit of trouble with my up arrows. And so what you see here is on the left during La Nina, a rainfall decile map. So it shows what the rainfall tends to do on average during La Nina years. And when you see all the blue colours, that indicates that you tend to get above average, you tend to get a higher decile, so above average rainfall across much of Eastern Australia, including your part of the world. Whereas during El Nino on the right, you tend to get lots of pink and reds, and that indicates that on average, you tend to get lower rainfall, including your part of the world. But it's not the only climate driver that affects climate in our part of the world. There's other things, including, for example, the Indian Ocean dipole. And so rather than the tropical Pacific being the centre of action, it's the Indian Ocean. And during a negative phase of the IOD, Indian Ocean dipole, you tend to get warmer water northwest of Australia, and that's associated with increased rainfall, increased convection, increased rainfall over Australia. Whereas during the positive phase on the left, again, you tend to get cooler water to the northwest of Australia. Again, it changes the convection and it moves the convection away from our part of the world to the west of the Indian Ocean, and that tends to give rise to reduced rainfall over many parts of Australia. And in fact, on the left, it shows again another decile map averaged over all of the IOD positive, Indian Ocean dipole positive years. And again, you see lots of pinks and yellows indicating that during those positive phases, much of Australia tends to get lower than average rainfall, whereas during the negative phase, you tend to get above average rainfall in many locations across Australia, including your part of the world. And associated with increased rainfall, you tend to get cooler temperatures. During the negative phase, and during the positive phase, you tend to get less rainfall and higher temperatures. Now, there are a number of other climate drivers too, and I notice that there's a lot of interest in keeping track of those individual climate drivers. But if you're interested in what's going to happen over the coming season, for example, the Bureau does the job of bringing together all of those modes of variability to come up with an outlook for what rainfall might do over the coming week, 2 weeks, month, 3 months. And what this shows is the outlook, the rainfall outlook for the coming 3 months, coming 3 calendar months, November, December, January. And you can see what this shows is the probability or the chance in percentage of exceeding the median rainfall amount. And if nothing's going on in the climate system, then there's just as much chance of being above the median as there is being below the median, 50%. Whereas if there's something going on, and there is at the present time, then that probability can shift away from 50%. And so you can see that in much of the country, the probability of rainfall being above the long-term median value is increased. It just so happens that in your part of the world, the probability has shifted the most. So there's at least in many parts, an 80%, 70 to 80% or higher chance that the rainfall during November to January, on average, averaged over the whole season, will be above the long-term median. And I've used to work in the National Climate Centre when we used to disseminate these outlooks, and every now and then you would say there's an increased chance that the rainfall will be above the median. And that would then get converted to, oh, the Bureau said it's going to rain a lot. Whereas that's not what the Bureau is saying. The Bureau is saying the chance of it being above the median is increased, and it's increased quite significantly this time because it's above 80%, as I said, in parts. But that still means that there's a 10, 15, 20% chance that it will be below. So that's one of the difficulties of using this sort of information, that the Bureau doesn't give categorical information like it will do this or it won't do that. They always associate it with probabilities or chances. And the reason they do that is because the climate system, yes, there are these drivers that can help give us a degree of predictability, but the climate system is partially a chaotic system. And chaotic systems have number of important characteristics, but one of them is that they have a very acute sensitivity to initial conditions. And so when you start off a forecast, you'll take a model and you'll tell that model what the current conditions are, and then the mathematics of that model will then generate a prediction. But it turns out that even a tiny, tiny, tiny difference in the initial conditions will give a somewhat different forecast. And the forecasts start to diverge greatly as time goes on. And so we don't know perfectly what current conditions are. We know them fairly accurately. We don't know them exactly. And so that little bit of uncertainty leads to, in part, uncertainty in the future. And so that's why the Bureau issues climate outlooks and rainfall outlooks in terms of probabilities or chances. Now, so far we've talked about interannual variability from year to year. We saw a bit of decadal variability in those earlier plots, decade to decade variability. But this is showing variability, again, natural variability, completely natural, on much, much longer timescales. So this is looking at an important quantity, the concentration in the atmosphere of carbon dioxide, back 800,000 years to a period up to close to where we currently are now. And so you can see that there's been an enormous amount of naturally occurring variability, and this has profound influence on the climate system associated with ice ages. So you can get big changes in sea level, temperature, and it's all completely natural. So you can see that not just from year to year variability from things like ENSO, but even on these much, much longer timescales, naturally occurring variability is critically important to climate on Earth. And I might say in Benalla and the Goulburn Valley and adjacent districts. And how do we know this? We know it because some fantastic scientists and technicians have drilled cores through ice in high latitude locations, Greenland and Antarctica. And what happens in Antarctica, for example, is it's so cold down there that all the snow that falls stays there. It doesn't melt. What it does, it melts under pressure, but it doesn't run off. And so the air that gets trapped in the snow gets trapped in these ice cores. So you build up after century after century after century, millennium after millennium, massive amount of snow, and then it gets pressured down, turns into ice, and the ice bubbles get trapped. And so what people do is drill these cores down. Essentially, the further they drill, the further back in time they're going, and then they analyze the air trapped in those bubbles. And so that's why we have these magnificent time series of what the concentration of atmospheric carbon dioxide was thousands and thousands of years ago. And one of the most important labs in the world happens to be in Melbourne, down in suburb not too far from me. So I think that they've done some fantastic work. So just to sum all of that up, the facts are these. First, natural processes can drive changes in climate on all timescales, not just from year to year, but for thousands, even hundreds of thousands of years. Natural variability is extremely important to climate in Australia, including Goulburn, in the Goulburn district. So that's the past. Has the climate changed? Well, we've already just had a look at this, natural variability. And one thing I didn't point out, I touched on it, but I didn't quite say it, was that, yes, this time series comes up to near present, but it stops before we get into the Industrial Revolution. Now what we can do is say, okay, what's happened to the concentration of carbon dioxide in the atmosphere since the beginning of the Industrial Revolution? That's what it looks like. On the same scale, it ticks away for about another 1800 years, and then it spikes up since the beginning of the Industrial Revolution, and that's because of human activity, including burning of fossil fuels. So you can see that through the burning of fossil fuels and other human activities, the concentration of carbon dioxide in the atmosphere has spiked up. So it's the concentrations we're now seeing in excess of 400 parts per million are larger than what we've seen for over 800,000 years. That's a fact. And as we know, carbon dioxide is a greenhouse gas. And so if an important greenhouse gas like carbon dioxide is increasing, you would expect the world to warm up. And that's exactly what's happened. So this shows, again, a plot of temperature, global average temperature anomalies. So you remove the long-term average, shows that the blue bars, it's below the average, red bars above the average from 1880 through to the end of 2020. And again, you see lots and lots of variability. but you see a trend to higher temperatures as time's gone on. And if you look more closer to home, this is the same sort of thing, but for Australia. So this is the Australian temperature anomaly. And you can again see that there's lots of below average values earlier in the 20th century. But then as you get towards the end of the 20th century and the beginning of the 21st century, there's lots of variability, but you see this underlying trend to higher temperatures across Australia. And if you look at trends across Australia, they're all over this period from 1910 to the end of 2020, they're all positive. So in other words, the whole country's warmed, including the Goulburn Valley. Another thing we've seen is an increase in the frequency of extremely high temperatures. So what this shows is how many days per year did the Australian continent reach the top 1% of values. And so you can see that, yes, it used to occur every now and then in the early 20th century, but now we're seeing it much, much more often. So we're experiencing high temperatures much, much more often than we used to, consistent with the warming patterns that we've seen in the previous slides. So some additional facts: the planet has warmed up and atmospheric CO2 concentrations are higher than they've been for at least 800,000 years. Now, why is it that scientists link increases in carbon dioxide in the atmosphere to global warming? And I already mentioned the greenhouse effect, and that's the reason why we connect those two things. So what I'd like to do now, if I can, is to stop sharing, and then hopefully you can see me again, and then to outline, to give you the simplest possible model of the greenhouse effect that you'll probably ever hear. So let's suppose that the radiation from the sun, let's suppose at the bottom of the screen is the surface of the Earth. So you've got radiation from the sun, gets absorbed by the surface of the Earth, and then the surface of the Earth then warms up. And everything in the when things warm up, they give off long wave radiation. So long wave radiation is a genuine, it's a physical thing, it's a genuine thing, but you can't see it. It's not visible to the naked eye, but it's very, very real. And the more you warm, the more the surface of the Earth warms up, the more long wave radiation is going to give off, pass through to outer space. And so the radiation comes down from the sun, the Earth warms up, gives off long wave radiation, warms up until it reaches the point where the amount of radiation it's getting from the sun matches the amount of radiation it's sending to outer space, reaches a nice equilibrium. But the trouble with that theory is it omits the atmosphere. What's really happening is radiation passes through the atmosphere, gets absorbed by the surface of the Earth, and then the surface of the Earth gives off long wave radiation. Some of that goes through the atmosphere to outer space, but some of it doesn't. Some of it gets absorbed in the atmosphere because the atmosphere contains greenhouse gases. And so what happens is, as I said, if something warms up, it gives off long wave radiation. So the atmosphere warms up, it gives off long wave radiation, some goes to outer space, but some comes back down to the surface of the Earth. So because of the greenhouse effect, the surface of the Earth is getting a double whammy. It's getting radiation directly from the sun, but it's also getting additional long wave radiation from the atmosphere. And so the surface of the Earth warms up. And what humans have been doing has been increasing the concentration of greenhouse gases in the atmosphere. And so that second whammy is now packing a stronger punch. And so inevitably, the planet Earth has warmed up more than it would have if it wasn't for human activity. So there you go. That's the simplest explanation for the greenhouse effect. But you, of course, realise that in order to understand what's happening and what's going to happen in the future, you shouldn't really do it waving your hands around like a lunatic. You really do need to think about things like, well, hang on a minute. Aren't there clouds? Don't they play a role? What about snow? Is all of the radiation from the sun going to make it to the Earth? Once it makes it to the Earth, is some of it going to be reflected? What about the oceans? What role are they playing? What about the winds and sea ice and snow at high latitudes, etc.? Surely you need to take all of that into account if you're going to work out what's going to happen to the planet Earth in response to increases in greenhouse gases. And if you said that, you would be perfectly correct. But fortunately, what we have are climate models. And climate models are mathematical models that represent the physics of the climate system. So you have equations for the ocean, for how much heat is in the ocean. You have equations for how much salinity is in the ocean. You have equations that you have terms in that mathematical model that represent the winds and rainfall and so on. And the interactions, importantly, the interactions between the atmosphere, the ocean and sea ice, for example. And so these models have been developed over the last 50 years or so. And so these are what we use not only to do seasonal outlooks in the Bureau these days or weather forecasts, they're also used to try and work out, well, what's the impact of increasing greenhouse gases on the climate? And I think taking into account the mathematics and the physics and technological advancement that's underpinned these models, I think that the development of these models represents one of the greatest achievements in human history. But having said that, we shouldn't get too carried away. The models are fantastic. They're the best tools we have to understand and project what's going to happen in the future, along with the observations, but they're not perfect, especially when you get down to small scales. So we'll come to that issue a little bit later. They are nevertheless magnificent tools that we can use. And one of the things we can use these tools for, these climate models, is to work out, well, how much warming should we get because of the increases in greenhouse gases that we've seen? So you can take these models and you can force them with natural processes like volcanic eruptions and variations in solar activity. And if you do that, you get that green line along the bottom. So we've got lots and lots of models around the world. So all of the modeling groups all do these sorts of experiments, and then we put all that information together. Well, that's what the IPCC did, and that's what you get if you force these models with natural processes. And by the way, that shading is because of the internal natural variability. All these models have their own El Ninos and La Ninas and SAMs and IODs, etc. But you can see that the observations in black here, there should have been a major warming event. But if you only force these models with natural processes, you don't simulate that warming, the warming that's been observed to occur. However, if you take exactly the same models and you also add the human elements, so you put in increases in greenhouse gases, for example, then you start to do a much, much better job of simulating the long-term warming that's occurred. So in summary, climate models can't simulate observed warming if forced by natural processes alone. However, climate models can simulate the observed warming if anthropogenic or human forcing is added, and in particular increases in greenhouse gases like carbon dioxide, but also things like methane. So that's a big reason why the climate has changed in recent times. And we saw before the Industrial Revolution, there are natural processes that can also play a big role in changing climate, but it just so happens that humans have now added another forcing term that can change and has changed climate. So that's the past. So let's now look at what might happen in the future. Now, in order to use climate models to project what's going to happen in the future, you need to tell those models what's going to happen to future concentrations of greenhouse gases. And the fact of the matter is, no one knows for sure what's going to happen to future concentrations of greenhouse gases because we don't know what's going to happen to future emissions of greenhouse gases. And so what scientists do, so there's a lot of discussion in the media lately, or the last year or 2 years, or even 10 years, but especially in the last year, in the last few months, about the Paris Agreement, which is an agreement which Australia signed up to reduce net global greenhouse gas emissions with the aim of keeping global warming well below 2 degrees Celsius and hopefully as close as 1.5 degrees Celsius as we can get. But we don't know what's going to happen, let's face it. So what scientists do is we consider a wide range of scenarios, some which have very marked and sustained reductions in greenhouse gas emissions, whereas we have other scenarios where the Paris Agreement is a complete failure. The countries around the world don't adhere to it. They keep pumping out lots of greenhouse gases. And so then you put that into the models and you can see what's going to happen to temperature and also what's going to happen to all those other climate variables, what's going to happen to the winds, what's going to happen to rainfall, what's going to happen to ocean, what's going to happen to sea level, etc. So that's what we need. And we do have those scenarios available. To force the climate models. And the most recent Intergovernmental Panel on Climate Change report came out in August, had this plot, and it shows, not surprisingly, that the more we emit, the warmer the planet's going to become. So this is the global average surface temperature anomalies relative to the latter half of the 19th century. So you can see it starts off, the anomalies are pretty small, and then it gets bigger and bigger, depending on what happens to global emissions over the coming century. So you can see that some near the bottom, or the very bottom one would be consistent with the Paris Agreement, whereas the ones near the top would be consistent with a failure for governments around the world to meet their obligations under the Paris Agreement. And so the world warms up by up to something like 5 degrees Celsius or even more, whereas the other ones, the warming tends to be more likely to be below 2 degrees Celsius. For some reason, my arrows aren't working. Sorry about that. And so one thing we can do with these climate models is look to see what happens at various degrees of global warming. So let's suppose that international negotiations are successful and the global warming is restricted to 1.5 degrees Celsius. That's the plot on the left. So you can see that even with the global average temperature increasing by 1.5 degrees, there's quite a wide range of temperatures experienced around the world. So in other words, there are regional contrasts in the amount of warming you get. And you can see from the 1.5 that the Arctic tends to warm up more than other locations. And similarly, you can do the same thing. Similarly, you can do the same thing for 2 degrees global warming and 4 degrees global warming. And the pattern doesn't change that much, just the numbers do. They're all roughly the same pattern, but the numbers just get bigger and bigger as the global average temperature gets bigger. And a couple other points you can probably make out, if you look at the 4 degree one, it's a bit more apparent, is that the land tends to warm up more than the ocean. So the land tends to warm up more than the global average. And if you look at Australia, the interior tends to warm up more than the coastal regions. So what does this mean for Australia, Victoria, and the Goulburn region? Well, let's begin by looking at projections from the same sorts of models, but for cool season rainfall. So this is rainfall. You can think of it as winter, spring rainfall, not quite. It's actually from April to October averaged. And so what this shows is a complicated plot, but it shows the rainfall projected from the models out through to through to the end of the current century. And if you concentrate on the red dots, that's what the average is across all these models. I think we have about 30 or 40 different models contributing to this plot from around the world. So what we did was we averaged them all up and said, okay, we look at just Victoria and average rainfall over Victoria. You find that you tend to get lower and lower rainfall as the century unfolds if you get a high emission, if you use a high emissions scenario. And that's the red. If you use blue, which is sort of an intermediate scenario, it tends to get drier and drier, but not as dry. And if you use the green one, which is getting close to what would happen under a Paris Agreement, yes, you get drying, but it's not as severe as it would be under one of the high emission scenarios. But you can also see that there's quite a spread. That is part of the spread amongst the models. So what can happen in some models are more sensitive to the increase in greenhouse gases than others, so they dry more. And the other thing is all of these models, as I said before, have their own variability, their own ENSOs and their own Indian Ocean dipoles, etc. So they exhibit variability. So what you actually end up getting is somewhat uncertain. There's a big chance that you're going to get less rainfall than what we've had in the past, but you're not 100% certain. But you can't, it'd be imprudent to dismiss the likelihood that you're going to end up with less rainfall. Now you might think, oh, well, how much less rainfall? Well, in order to try and put it into context, what we did was to also show, using those dashed horizontal lines, some dry periods that occurred in the recent, historical record. So we looked at the World War II drought, the Millennium Drought, which occurred, towards the end, around the turn of the century, and the last 22 years, which was a dry period. And you can see that relative to the Millennium Drought and the dry 22-year period, that becomes sort of like average conditions. So you'd be sort of hoping for above average rainfall towards the end of the 20th century. If you didn't, you're going to get just as dry or much, much drier than the recent 22 years. And just to give you an illustration of how dry it's been, if you look over the 22-year period, this shows the April to October rainfall in each year from 1900 through to 2020 in northeast Victoria. So again, there's a huge amount of variability. So these are anomalies this time, to remove the long-term average. And so you can see, yes, there's lots of variability. Some years you get well above average, some years you get well below. But if you look in the last 20 years or so, it's been predominantly below average. So under that worst scenario, if greenhouse gas emissions continue to increase on their merry way, or not so merry way, then that would be an average set of conditions, which is obviously not something we want to see. And so it provides further motivation for hoping to see that the meeting that they're going to be held in Scotland later this year to reach agreement on further reducing emissions would be successful. So that's mean rainfall. Let's now look at, so on the left-hand side, this shows what rainfall projections are associated with 1.5 degrees Celsius at the top. So if you focus just on the left-hand column, and we'll come back to the right-hand column in a minute. So these show the projected changes in annual rainfall for 3 different warming levels. So the top left shows the average across all models of what the percentage change in annual rainfall will be if global average warming is 1.5 degrees Celsius. The middle panel on the left shows the percentage change in annual precipitation in a 2-degree warming world. And the bottom panel on the left-hand side shows the percentage change in annual precipitation in a 4-degree global warming world. And again, you can see that the patterns look very similar, but the numbers increase in magnitude. And you can see that there's a tendency for parts of southern Australia for the rainfall to decline. Whereas if you notice that with rainfall, you can get increases and you can get decreases. Warming tends to occur everywhere, but rainfall can go up in some places and it can go down in other places. And it just so happens that, especially during winter, spring, the models project a decline in rainfall over much of southern Australia. Now, the plot on the right is also precipitation, but it's extreme precipitation. So what the IPCC did here was to only look at those days that set the highest amount of rainfall in a particular year. And then they looked at how is that going to change in the future. And what they find is that over most of the land across the world, including most of Australia, that the amount of rainfall you get on the wettest day of the year tends to go up. So on the one hand, you've got in southern Australia a tendency for the averages to decline, but you're still going to get punctuated. Those dry days potentially going to get punctuated with days that are just as wet or perhaps even wetter than they used to be. Now, we've got more information about what can happen in your part of the world from this report that I referred to earlier, produced by the Victorian Department of Environment, Land, Water and Planning in conjunction with CSIRO. And they concluded the following. They concluded that maximum and minimum daily temperatures will continue to increase over this century, and they assign a very high confidence to that statement. So that wouldn't come as a surprise given what we've just been looking at. And they conclude that by the 2030s, which is not that far away, increases in daily maximum temperature of 0.9 to 1.8 degrees Celsius are expected, and that's since the 1990s. So that's not very, not that distant. They also concluded that rainfall will continue to be very variable over time. So all of that variability we talked about previously at the beginning of the talk, that's not going to go away. That's still going to be a major driver of climate variability in your part of the world over the coming century. It cannot be ignored. But over the long term, it's expected to continue to decline in winter and spring, medium to high confidence, and autumn, low to medium confidence, but with some chance of little change. So in other words, in addition to that variability, there's there's expectation that rainfall on average is going to decline, particularly during winter and spring. However, as I mentioned, which is true over most land points, the vast majority of land points around the world, extreme precipitation events are expected to become more intense on average through the century, but remain very variable in space and time. So they're rare events, so you're not 100% sure if it's going to pan out that way, but it's increasing the risk that that's what's going to happen, increasing the likelihood that that's what's going to happen. And the final conclusion, major conclusion they make is that by the 2050s, the climate of Shepparton could be more like the current climate of Griffith in New South Wales. So a bit drier and a bit warmer. And that same report then goes on to provide a lot more detail on this information. I wasn't quite sure how much you needed to know in the next session, so just give you a little bit of detail on that. So what this shows is the projected temperature changes as a function of time in the 2030s, 2050s, 2070, 2090 from this report. And they conclude that projected changes, and these are all relative to the period 1986 to 2005, just to confuse you even more, for annual mean temperature for so-called medium emissions at the top and for high emissions at the bottom. And so through the Paris Agreement, we're hoping we won't see the high emissions. And if the Paris Agreement is even successful, the warming might not even be as large as those medium emissions plot. But you can see that if the high emissions were to occur, then this part of the world will warm relative to recent past of something like 3, 4 or 5 degrees Celsius relative to what it's been in the past. The pink ones, they've taken from a certain set of climate models. The red one is taken from the latest generation of models. So you can see there's a little bit of difference there. So there is a degree of uncertainty, but you can see that they all warm up without exception, and the warming gets greater and greater as time goes on, and the warming is greater if the emissions are greater. And you can show the same sort of thing, but this time for percentage change in rainfall. And this is annual mean rainfall. And again, there's a lot of variability amongst models that reflects two things. One, that some models dry out more than other models, and some models don't dry out much at all. But also, all of the models have their own natural variability. But again, you can see a general tendency, not as clear as the temperature, but a general tendency for the rainfall reduction to be larger under the high emissions than the medium emissions, and to be larger as time goes on under these emissions. And you can see that the median values, so half the models have values lower and half the models have values higher. Under the median under the high emissions, the median is something like minus 24% reduction. So clearly we do not want to see that scenario emerge in the real world. And the last point I wanted to make is that it's really important for that reason I just outlined, but for other reasons, that keeping warming as low as possible is a critical factor. So if we consider the Great Barrier Reef, because it's a fairly stark example, for example, this is what the conclusions of the recent IPCC reports were. The majority of warmer water coral reefs, which is what the Great Barrier Reef is, that exist today, will largely disappear when global warming exceeds 1.5 degrees Celsius. And they conclude that with very high confidence. And reef restoration, which is another word for climate change adaptation, reef restoration options may be ineffective if warming exceeds 1.5 degrees Celsius. So in other words, it's important that we do climate change adaptation. We think about what's going to happen and we change our systems to manage things. But in this particular instance, and it's not the only instance, the warming and the changes may be so great, and the associated change in ocean acidification in this case, that adaptation isn't sufficient, that you still end up with massive changes in biodiversity, so that the species and diversity of remaining reef coral communities are projected to differ from present day reefs. So that's a very diplomatic, conservative way of saying that you're going from a beautiful, very highly diverse ecosystem to one which is very bland, colourless, and, to be frank, is not going to attract tourists from around the world. So in summary then, we've seen that natural climate variability will continue to be a major driver of Australian climate variability, as it has in the past. And that's on all timescales, from year to year, decade to decade, generation to generation, and even longer. However, we've already seen that human-forced climate change is underway. And so an important implication there is that beware of using the past as a guide to the future. And furthermore, the greater the warming, the greater the associated changes and the greater the impacts. And the more likely we're going to experience things, and ecosystems will experience things that they cannot cope with or which humans cannot properly manage. So clearly, markedly reducing global greenhouse gas emissions and preparing for the inevitable changes, because some of these changes are inevitable, no matter what happens with international negotiations, for the inevitable changes ahead, are both crucial to managing climate. It doesn't make sense to do one without the other. And as I've mentioned, some systems may go beyond their management limits or their ability to cope if global warming exceeds 1.5 degrees Celsius. And the warmer the planet gets, the more likely and the more prevalent that situation will be, not just for managed systems, but for unmanaged, natural systems or ecosystems. Thank you very much.